Hi, my name is Chad Schmitke, and I want to talk today about simulation and how it can provide insight and perhaps better decision making in the roll-to-roll industry. My background is in simulation. I've been doing this for almost 2.5 decades, and I currently sit as the Senior Director of Solutions at Maplesoft, which is a convoluted way of saying I work very closely with our applications engineering team and our customers to provide solutions. I also lead the development of our engineering simulation software, MapleSim. But enough about me. I'll tell you a little bit about my company. Maplesoft is a company that started as a startup just under 4 decades ago. We've since grown into a global company, and we have 3 main flagship products, Maple and MapleSim, which are primarily interested in mathematical and engineering calculation and analysis, as well as MapleSim, which is our multi-domain system-level modeling tool. I'll talk a little bit more about what I mean in that shortly. If you look on the right, that's not all web handling. There's all kinds of domains listed there, and it kind of maps the trajectory our foray into the engineering world has gone, starting with aerospace and automotive, then into machine design, and then finally following up now in this web handling world where we've been working and active in the last 4.5, 5 years. So I'm going to be using the word simulation a lot in this presentation, and I want to make sure that we all have a common understanding of what I mean when I say simulation. So, broad picture, you can think of, people talk about plant-wide simulation. That's not what we're talking about today, where you're interested in things like throughput or sequencing. Things are monitoring discrete events. Often these simulators have a game engine that's, as bottles bump into each other, trying to mimic how these, so you can make decisions about sort of overall plant layout, not what we're looking at. On the other side is part level simulation, finite element. People are maybe more familiar with this. This is where you're looking at detail into the forces and tensions and strains in a given part. That's a little too detailed for what we're looking at. We're looking sort of a middle scope, which is the machine level. And I've shown an example of a web handling machine there, but that could have 100, 200 rollers, no problem. But the idea is that we're mostly interested in the tensions in this design in the machine direction. We assume things are homogeneous in the cross direction for the most part. And we're answering questions like, what are the tensions? What are the strains? How much does the dancer move? What is the torque on my driving rollers? Things like that. Okay, now a little bit more detail on 1D simulation. The way that you describe or present the system is often blocks that you attach together. Those blocks represent physical components. So here you see we've got wind drums and dancers. There's an SRAP roller there, load cell for the control. You can see I've got motors listed in here. There's also control signals in here. And so what I want you to take away from the diagram is that not only do you have your standard components that you'd see on a web line, but you also have the control signals, that you can put that right in the simulation. You also have different domains you can add. In this case, the dancer has just a spring damper in it, but that could be driven by a pneumatic system, which could be included in this model as well. So different domains, and you can encompass them sort of all together. Once you simulate the model, I should say before I get there, to change parameters or to investigate a model, you can add parameters and modify things. So for instance, the web itself has the parameters of width and thickness, density, Young's modulus, Poisson's ratio. Those are properties of the web that you change, you enter in, and then when you run your simulation, you can see how it affects that simulation. You can, for your control signals, you might say, what is my tension on my unwind and my rewind? Or you could say, what is the friction in my SRAP? Things like that. You make adjustments as parameters that you enter, and then you rerun a simulation to see your results. Now, when you rerun your simulation, we will automatically generate a 3D visualization. Again, it's a 3D, but really it's considered homogeneous in the cross direction. You can get plots of anything you want in the model. Everything's available to you. And it can start to give you insight into how this system's going to behave. For instance, one of the nice things about a 3D visualization is you can immediately see things that might be harder to tell just from plots. So you can see if I run this material, exact same structure, but with a softer material, sorry, this machine with the same structure, same control setup, but with a softer material, you can immediately see the sagging that goes on. This is the kind of comparative analysis you might do in a 1D simulation. There's also this additional model I've included here. It's just a simple sequence of rollers, but again, it shows this ability to play with the model, and 1D simulation models are generally very fast. This machine or this model is running faster than real time. We're actually slowing it down here so that you can see the propagation of the tension going from green, a lower tension, to a higher tension in red as we add rollers to the system. So the takeaway here is the kind of simulation I'm talking about includes many domains, control and otherwise. It includes 3D visualizations so you can sort of gain insights or see how things are moving along. And it's fast to run. It's quick and you can get results quickly and run numerous simulations. All right, so now you have an idea, I hope, of what I mean by simulation. What does simulation provide us with? Well, simulation provides us with the same things it's provided other industries for decades, right? In automotive and aerospace, that's where it was first really started to get used. It provides this virtual test bed where you can make rapid changes and try out different designs. It's a safe environment to do this, of course, because it's in the computer, so you're free to try out what-if scenarios. You can quickly generate them and analyze them without the overhead of having to build that system physically. But it also gives engineers a deep insight into models. So it's not just that they'll be able to run all these tests, it gives extra information because you can probe and look at anything. And so the same way that simulation has brought advantages and been a driver to these other industries, it can do that for the web handling industry as well. And one thing I want to talk about sort of near the end of this presentation is that this can also help outside of just the time and cost savings. It can foster innovation and collaboration and actually, for lack of a better term, unlock your company know-how. So let's talk first about what the core thing that simulation does when we think about it, and that's the idea of saving time and money. It's a really convenient and cost-effective way to run tests. So when you want to run a test, right, you have a solution, you have an idea in your head that you want to run, you then have to get somebody to implement. So you have to either draw that out or you go down and adjust the machine yourself. Some technician will take that and perform those steps. They will then record the results, hopefully at the frequency that you need to see the information that you're looking for. And then you will get that analysis back, make a decision, and run another test. And that looping happens, but there's expenses involved in that, right? There's the technician's time, there's all the material loss, there's the machine time. If that machine's in production, it actually have to be pulled off production and go. And in fact, if the machine doesn't exist, you have to build a prototype to play around with in order to do that. So there's lots of cost and time and money that goes into that. Whereas on a virtual simulation, there's no material. Everything exists inside the computer. You don't have to involve a technician to make changes. You don't have to, book time on a machine. Everything's just on the computer, and you can run that simulation and get the feedback immediately. So in that sense, simulation is a really cost-effective way of running tests. But and maybe a little bit more detail, when we say cost-effective way, what are some of the advantages of being able to run these tests so rapidly? Well, first of all, when you're debugging complex problems, right? It allows you to just quickly go through. I talked about those what-if scenarios, right? What if there was an eccentricity in one of the rollers? Would that give me what I'm looking or what I'm seeing on the machine? Or if there's a slipping that's maybe not visible to the naked eye, is that the kind of thing that's producing what I'm seeing at the load cell? Or if a roller bearing was stiffer, what would that affect? So you can quickly play with the machine and see how it responds to different, let's call them different situations, and that gives you feedback and insight into what you're doing. You can modify designs, right? Very quickly, you can move where a roller is, or say, what if we used a linear dancer rather than a rotary dancer? Or what if we used a different control strategy? How would that affect the tensions or the way things move in this system? These are things that can be tested and done very quickly in a virtual setting. And finally, robustness testing, right? If you can rapidly run tests, you can try out your control system and try the system out with a variety of different materials. If it's softer to a stiffer material, what happens if it was more slippery, and there was slip on the rollers? Is my control system able to handle that? These kinds of what if or robustness testings can be done quickly. But if we only think of virtual testing as a way to do normal testing faster, we're missing something really important that testing provides. And I want to unpack that a little bit in the next slide. When you run a physical test, and let's all agree, physical tests are the gold standard, right? They encompass all the unknowns, all the variables, everything's involved. If you get the physical test running correctly, your machine's running correctly. However, that same advantage of including everything means that you're also including things that are uncontrolled or perhaps an unknown to the model. For instance, operator consistency. You've asked them to run a bunch of tests. Are they doing it the same way each time? And is it the same operator? Maybe someone else came in and ran some of the tests. Are you getting the same? Is there an unknown or a difference being added in that you're not accounting for? Machine consistency. If you're lucky enough to have a machine that you can be working on between tests, did somebody else need to use it and tweak some of the knobs and dials, and now it's in a slightly different state than it was when you ran those previous tests? And then finally, even things like material consistency. You ran a bunch of tests, and now we had to swap rolls, or maybe the test was run in the morning and things were colder and the material was a little bit stiffer. All of these things are unknowns that will influence the test results that you get. And when we talk about test results, that's another challenge that real testing provides, is that you have a limited number of things that you can be looking at. There's only so many load cells or encoders that you can be pulling data from. And if you want to try and get one in another area, it's time to set that up. But again, you just get data in that one spot. Virtual testing, obviously, is different in that when you see a result and you change something and you run another test, it's guaranteed that the only thing affecting the new result is the change that you made, which helps you isolate what your changes in a certain area perform, how they affect the results that you're seeing. And talking about the results you're seeing, you also now get to see anything you want about the system. Any strain, any tension in any web. You can see any roller, how fast it's moving, how it moves, how a dancer arm moves, what its velocity was, what were the torques on the drive rollers. All of these things are available for you to investigate after the fact. So whereas traditional testing does give you a broad spectrum of things that you can investigate, and it's the gold standard, it does include unknown variables that are not controlled, and maybe you don't know that they're changing. And it does sometimes make it hard to make inferences between what's been changed in a test and what results you're seeing from a test. And this kind of boils down to one of the big things that virtual testing can provide, and that is insight. Insight to get to a solution. So there are people at companies that they look at a machine, they look at a result, and they see the information coming from that load cell, and they look from what they can see with their eyes when they're watching the machine run, and it's like they can see behind it and understand the machine, and they've got a good idea of what's going on. Maybe they're really familiar with these machines. Maybe they've just got 3 decades of experience in the industry. They can get up to running and understand what's happening. It's almost like if you think of the machine as a puzzle, like I've got a Sudoku puzzle there, they've got more numbers filled in, right? Because of their years of experience, they've got lots of numbers filled in, which makes it easier for them to investigate and solve the puzzle. But even for them, and certainly for people that are new and coming on, it's really helpful if more of that puzzle were filled in. And simulation provides a consistent, systematic way to gain insight into machines, which is kind of like filling in more pieces of the puzzle so that you don't have to waste time on tests that you already know are precluded based on the simulation results you've looked at already. You don't have to spend time on them. Or you have a better understanding about the relationship between the bearing friction and your drive and control system. I'll talk about an example of that later on. So insight not just allows you to, virtual models don't just allow you to run lots of tests, but they also allow you to get more information out of those tests. Okay, So I said that simulation was a game changer in these other industries and that it can be in the roll-to-roll industry as well. And I've talked a little bit here about what I mean when I said the what-if scenarios, what I mean by deeper insight. But how does that have an influence on your organization? So when you think about, first of all, let's think about innovation, right? If you have an environment where engineers can rapidly test things without it being super costly, they can immediately get feedback on the information, and from any test they run, they get consistent, systematic feedback. It's going to have a positive effect on your innovation. They're already solving problems in innovative ways today. Giving them more consistent information is only going to improve that. It also provides a way for people to talk about designs, to get more people involved in a design. Now, you can imagine, you can talk about a drawing, or you can talk about something that's got graphs and plots, and someone suggests, what if we did this? You can very easily make that change, see how the system would be affected. It engages more team members. It can also potentially be used by your sales or presented to your customers, so they have an idea of what you're working on and the challenges that their machine has. And then finally, we talk about organizational knowledge in simulation. I mentioned that there's some people who look at that puzzle and they've got everything filled out already in their heads. It's not true for the newcomers coming on board. And let's be clear, nothing replaces the 3 decades of experience, but everybody has the luxury of coming on board with that. And so having your machines and having them set up that people can see how they run, see the inner workings, how that tension propagates, and what happens when they change knobs and dials, can give them an insight into it and get on board faster for maintaining, designing, and perhaps extending a given machine. It also helps capture knowledge when, if you guys build a machine and then you go away from it and 5 years later you're looking at it again, it's the same idea. You want to get up to speed on it, but perhaps the person who made some of those decisions isn't there anymore. Now you've got a record of how that machine operates and a quick test bed to play with it as you're investigating the new problem on that machine. So, talked about innovation. I've talked about how it can enhance workflow, this idea of capturing a company's knowledge. I think the next important thing to talk about is how maybe are our customers using this today, right? So some examples of things that our customers are doing with simulation today, or how they're trying to integrate simulation into their processes that they currently have. So the first one is from a large printing manufacturer. They wanted to first get their feet wet with simulation, right? So they've got printing systems, they've got complicated shuttles that have very complicated tension profiles going on. You can imagine as the shuttle's going back and forth. What they did is they chose to do as a pilot, where first they built one of their shuttles where they had already recorded and done tensions to find out if they could replicate what they knew their testing had provided. They were able to replicate, which gave them confidence that, hey, we're able to be successful with these models, we're able to do it, and now they use it as part of their subsequent design process when they're building new machines. Another battery manufacturer, and this one was, they were investigating a problem. I think they had been looking at it for 6 months, trying to track down where an unwanted vibration was coming from. There's a lot going on here, but effectively running the simulations allowed them to get an insight into their machine, what things were affecting it, what things certainly weren't causing that vibration, and allowed them to isolate where the vibration was coming from, and then provided a test bed for them to try different ideas virtually of how they were going to eliminate the vibration. This one's also interesting because we created, there's that component there of the 234. You see, we actually created that component for them so that they could specifically model phenomena that they were seeing in their system. All right, large print manufacturer again, and this is that idea of what-if scenarios. They had delivered a machine, it had had a poor behavior at the customers. They wanted to match and see if they could figure out what had happened. Simulation allowed them to say, hey, what if something got damaged in shipment? What if we have an eccentricity? Can we start matching the kind of results that a customer is seeing? And this sort of provided a testing ground for them before they had to go to the customers and physically look at the machine and start tweaking it and playing around with it there. This is one of those insight pieces where a customer had a model where when they ran the web one way, everything was great. They ran it the other way, they had sagging and slippage. And it wasn't until they looked at the simulation and could see the propagations of tensions, how things moved, that they were able to find out or understand the connection between the control structure they were using, their bearing loss issues, and the actual tension in the web. And then this last one is just a company who had a ton of experience with building web lines, but wanted to get into a new area. So they wanted to come up with a Z-fold web line concept for making batteries. So the ability to do rapid simulations allowed them to test different ideas quickly. It allowed them to sort of consolidate and say, we don't have a gut feel for this. Let's learn by building a bunch of models and learning what they provide or different ways of doing things, what that provides. And then eventually, for their first prototype, they use their simulation to give them an idea of what size motor they would need or what size actuators they would actually need to build with. Okay, I've gone through a bunch of examples from our customers here, but you can also go online and find more examples or find more nitty-gritty on how to do the modeling, right? What does it actually look like to use simulation to solve a problem from experts who have been in the field for decades, right? How can you use simulation to solve common problems? We've got papers. You can look all these things up online. We've also got training material. We just released our online training material. You can grab that off our website. Take a look at it. If you want, you can get a evaluation copy to examine that material with and see if it you can start to get a feel for the types of insight that simulation can provide. All right. I talked about rapid simulation. I talked about how it can enhance culture, provide insights to your design workflow, how as a company it can help you onboard things. At this point, I think I'll wrap up. Thank you for your time and open the session up to questions. Thank you.
Question that you have is, what is the frequency response capability? For example, eccentric rollers or gears or motors that are not turning properly.
Sure. If I understand the question, it's what frequency can we capture in the simulation? Remember, the simulation behind the scenes is effectively a set of equations that are being solved, and the solver takes smaller and smaller steps to ensure that the accuracy is maintained during that integration. What that all means is if you've got a high frequency system or some high frequency mode activated in your model, that will be captured in the simulation, and it will take enough steps to make sure that that frequency is captured in the available data. You do sometimes need to increase the plot points. That means the number of points in your simulation result so that you can see it, but it's captured in the dynamics that are being simulated.
Okay, and then a follow-up to that is it possible to model slitting?
Yes, the slitting action is possible. However, the piece that we don't account for in our tool is the dynamics of the cutter and the web. That's not something that we maintain. You can have a web that splits off and is slit. In the model, we have those components, but it's important to understand that we're not looking at the slitting process, just what's happening to the web line as it's going through.
Got it. So for companies that are still relying heavily on a physical testing today, what's the practical first step to start simulation in their workflow? Like, what kind of data is needed to get started, building a model of a web line?
Sure. Well, I mean, you need the same data that you would need, or at least you need a subset at least of that data that you need for the real system, right? You need to know your roller sizes, you need to know where they're located. You need to sort of the web path layout, right? Your control strategy that you're going to use. All of those things you would put into the model, and you could build up the skeleton model. You won't have things initially, certainly like friction. You probably put an approximation in for that. Material properties, some people have them. Some people sort of say, I know it's within this range, and so they would run simulations within that range. So getting started, you need the basic information you'd need if you were going to design this thing outright, right? You can pull it from the CAD or the this whatever you were using to initially sort of design that layout. I should add that simulations can get you can add more information as you want to increase the fidelity of your model. It depends what answers you're looking for from the simulation. The first part of your question, or that question, Sangeeta, of how do
Mhm.
companies get started, I do want to circle back on that. It is, it's different for different companies, right? And I think what we've seen is that people often want to do a small project to start, which is really a proof of concept for them of can they be successful with the software? Can they see themselves getting answers and solving problems faster with the simulation? Um, it's it's rare that someone just sees it and says, "Yeah, we'll go full on into this." Usually, it's small steps to begin with, and then they feel confident. Like in some of those stories that I mentioned, they try a proof of concept, they see the success, they see that, yeah, we can get those answers, and then they're willing to move forward with using it as part of their design.
Mm-hmm. So, as a continuation to that, so what does the learning curve look like? Is it something that an engineer can just pick it up on their own, or does it require dedicated training? Do they need prior simulation knowledge? How does it look like?
So I remind everyone that I lead the development for the team that builds this software. So take everything I say with a grain of salt. The actual process of solving the problem is kind of the same, right? That what if scenario. The idea is that in software you can make those changes faster. And that there's been a lot of work done to make the building, the way those components are organized and how you can lay them out intuitive so that it's easy to build the system. The process of running a model and then looking at results, again, that's fairly straightforward. Where additional training would start to come in is getting sort of going to the next level with the software, right? How do I ask the questions? Or is there a different way that I can isolate this in the software? Or, man, I built something and I did something odd and the software gave me an error. How do I go about debugging that error? So there are some pieces that are related to you're using new software and you have to learn it. But there's a lot of pieces but it's the same process in some ways to what you were doing on the physical system.
Mm-hmm. So then, as a segue to that,
Yep.
how validated do these simulation models need to be before engineer can trust them enough to make real decisions?
It's a good question. So simulation, there's a quote that says that all simulations are wrong, but some of them are useful. And I like it because it points out that you always in a simulation have assumptions, right? I mentioned that real models are gold standards. They include everything. When we have a simulation, we are simplifying effectively certain things and bringing them in. Now, the things that we put in, we can be confident that the physics is being computed correctly, that the answer is correct based on what you've put in. The real question is, have I put in enough stuff? And that always depends on what kind of questions you're asking the simulation and what you're looking for. Um, yeah, I don't know that I have it's a longer answer for that.
Mm-hmm. I get you. And you also mentioned something about debugging issues of vibration or tension inconsistencies. How effective do you think simulation is in helping engineers or teams like pinpoint the root causes when you compare them with like a traditional physical
Yeah.
trial and error?
The real benefit that simulation provides is the ability to try things quickly. So if you're seeing some effect in your model, you can try it out in simulation and say, well, if this is an eccentricity or if this is a friction problem, if I modify that in my simulation, am I seeing the same kind of frequency of response that I'm seeing in my real system? And you can do that kind of testing quickly, if if only to sort of rule things out that you don't need to look at on the physical system, because it's possible the thing that's causing you the issue, you have it included in your model.
Mm-hmm.
So it's effective in helping you isolate certainly what is not the cause and where the cause probably or likely is coming from.
Okay. And another interesting question that popped up is, have you had any success building hybrid models that combine a virtual model with actual data from a physical web line?
Actually, that's a really important part of debugging systems that are running and are exhibiting a problem. Because one of the things you do is you build what we would call a nominal model. That's the model where you go from the spec and you build it and build the machine based on where all the rollers are and what they're, what materials they're made from. So you get the inertias for the rollers, etc. But then you take real data from a machine, wherever it's available, and then you run your simulation model against that data where you've got tuning parameters in the model itself that you can then use to tweak your model until it matches the data of the physical system. And this is where you can say, well, if I add an eccentricity, do I start to get closer to that data? Now, if you're talking about what sometimes in the industry referred to as gray box models, where you've got sort of some element of the real system that's empirical from data, and you're compiling that together. We do sometimes use lookup tables when there's parts of the system that we don't handle. You can put a lookup table in that says, here's the inputs, I've got these outputs, I've got this data that I've stored. So that can be brought into the model as well. But you have to understand then that that part of the model is effectively locked. It's always going to act the same. You have no knobs or dials in the simulation that you can modify it with.
Okay.
Not sure if I've answered the question they were looking at there, but we can follow up if they want more.
All right. Another question is, you've talked about capturing organizational knowledge.
Mhm.
How does simulation help preserve that? Especially like when a key engineer who's worked for years in a company is leaving, how can simulation
Yeah.
help?
So when a key engineer that's been working for years leaves, that's a huge loss, and there's no amount of sort of simulation model to just that make that simple and as if it didn't happen, right? But what a simulation model does provide, and especially if you've got models that have been worked on that system over time, is that when someone else sort of now takes on ownership for that and looking after it, they can go back and they've effectively got a richer history of, hey, we tried this. Look, here's a model of it and what the effect that we saw was. So you can get up to speed on a system much faster because you're seeing a visualization of sort of different instances of it when that machine either wasn't working or something was fixed. Um, Also, it's just having a model can help people again who are new to it get experience with it before they have to go out to the real machine.
All right. So I guess we just have time for that many questions, and we've reached the end of today's webinar. Thanks, Chad, for answering the questions that have popped up. If you have additional questions, please feel free to email them to webinars@maplesoft.com. Thank you, everyone, for taking time out of your busy schedules and joining us today. We hope you enjoyed Chad's session and see you soon. Thank you.